Okay, now we will start our study of the chapter 2. We will study continuous functions. Continuity, compactness, and connectedness. Okay, firstly, we will study continuity. The first section, continuous function. And maps, also called mappings. Okay. In single variable calculus, we have studied functions of this form, may be defined on an interval and take value in the real numbers. Okay, but here we will study more general functions. That is vector valued functions. So I will tell you what's vector value functions, also called maps. Okay, suppose A is a subset of Rn, and a map F from A to another Euclidean space Rn. This is called vector value function, also called maps. Of course, we have two maps. We have two map here. The meaning is different. The first map is a general correspondence. This means for any x take from the set A, we associate a unique y denoted by fx from Rn. So a map is a correspondence, a law to associate every element of A to an unique element of Rn. This is what the map means. Such a map is called vector valued function. But for simplicity, we also just call it a map. Okay. So the previous studied function is a very simple case of our function considered here. For this case, n is 1, n is also 1, and A is a subset. A is an interval AB, which is a subset of R. So this function is one. This function has one independent variable and one dependent variable. So this is the most simple case. But in our course, we will study functions which several independent variables and also several dependent variables. Okay. So suppose we have a function from A to Rn, defined on A and take value in Rn. Here A is a subset of Rn. Such A is called a domain of definition of this function. Okay. When are given a function like this, then if x is an element of A, fx will be an element of Rn. Depend completely by the choice of x. You take different x from A, you will get different fx in Rn, right? So since fx is a point in Rn, it has n coordinate. We can use fix to denote the ith coordinate of fx. So once we give x, you get the ith coordinate, which is a real number. So fix is a function of x. So our fx can be written in this way: f1x, fmx, because fx has m coordinate. Therefore, each fi can be considered as a function, a real-valued function defined on A. The value of this function A is exactly fia. That is the ith coordinate of fx, of the value of our vector valued function f at the point x. Okay, so because of this reason, usually we write very intuitively our f so our fx is a point f1x, fmx. So, but we will emphasize this distinction between f and fx. F is a function or map, but fx is the value of the function f at x. We will emphasize this distinction. You should you should have this in mind during your study. So we want to write f by its component. The f1, f2, fm are called components of our function f. Component of f. Components of f. So a vector valued function f is completely determined by its components. It has n components. Okay, this is our basic concept of vector valued functions or maps. Now we study the continuity. What is continuity means? Okay, continuity means once the independent variable are close enough, the corresponding value of the function will be also close enough. Okay, to describe closeness, a very simple and a very convenient method is using sequence. So we define the continuity of a function using the language of sequence, our definition. Suppose A is a subset of Rn, and A is a point in A, and f is a function defined on A and taking value in another Euclidean space Rn. Then we say that this function f is continuous at this given point A, if the following condition is satisfied. If fa xk converge to fa for any sequence xk in A such that the sequence converges to A. So this is very clear, very simple definition. Continuity at the point A. So let us have a look on this definition. Here, both A and every xk are points in A. A and xk are in the domain of the definition of our function f. Therefore, it makes sense to write fxk and fa. This is the first point. Okay. Secondly, we have already studied the convergence of a sequence in Euclidean space. Therefore, fk converges to A and fxk converges to fa. Both these two convergences make sense. Okay, so everything in this definition makes sense. Thirdly, we know that a sequence converges to a point A. Intuitively, a sequence xk converges to a point A means that the distance from this point to that point is smaller and smaller, or the point xk is closer and closer to the point A. So this definition simply means that once the independent variable of the function f is closer to the point A, the corresponding dependent variable, which is fxk, also very close to the corresponding value of fa, right? So this is the continuity of this function at this point A. In any case, our function will be continuous at every point of its domain of definition. So we have another part of our definition. The second part, if f is continuous at every point in A, then f is continuous on A, or just say that f is a continuous function. Okay, so this is the definition. Okay, now I will give you an example.